Hello viewers of Araatech. Today's topic is about BERT. BERT or Bidirectional Encoder Representations from Transformers is a revolutionary artificial intelligence model for language understanding. It's excellent at grasping context by considering words from both directions in a sentence. Using self-attention mechanisms, BERT weighs the importance of words based on their context, enabling precise representations. Pre-trained on vast text data, BERT learns language patterns independently and can be fine-tuned for specific tasks, making it highly adaptable. It's a leader in NLP tasks, driving innovation in artificial intelligence research. BERT's open source nature encourages widespread use and continual improvement in machine learning applications. Thanks for watching and don't forget to subscribe, like and share. Let's start our topic today. What is BERT? BERT, short for Bidirectional Encoder Representations from Transformers, is a state-of-the-art natural language processing (NLP) model introduced by Google researchers in 2018. It belongs to the family of transformer models, which are neural network architectures specifically designed for processing sequential data such as text. BERT is designed to capture the bidirectional context of words in a sentence, meaning it considers both the left and right context when generating word embeddings. This bidirectional approach enables BERT to produce contextually rich representations of words, allowing it to understand the nuances and complexities of natural language more effectively. Why BERT? Before the advent of BERT, many NLP models such as Word2Vec and Globe were limited by their inability to capture contextual information. These models typically represented words as fixed vectors, ignoring the context in which the words appeared. As a result, they struggled with tasks requiring a deeper understanding of language, such as sentiment analysis, named entity recognition, and question answering. BERT addresses these limitations by leveraging the transformer architecture, which employs self-attention mechanisms to weigh the importance of different words in a sentence. This enables BERT to capture complex linguistic patterns and relationships, leading to significant improvements in various NLP tasks. BERT's impact on NLP. The introduction of BERT has had a profound impact on the field of natural language processing, revolutionizing the way researchers and practitioners approach language understanding tasks. Some key impacts of BERT on NLP include improved performance. BERT has achieved state-of-the-art results on a wide range of NLP benchmarks, surpassing previous models by a significant margin. Its ability to capture bidirectional context allows it to better understand the meaning and semantic of text, leading to more accurate predictions. Transfer learning. BERT's pre-trained and fine-tuning paradigm has popularized the use of transfer learning in NLP. Pre-training BERT on large corpora of text data using unsupervised learning objectives such as masked language modeling and text sentence prediction enables the model to learn general language representations. These pre-trained representations can then be fine-tuned on specific downstream tasks with labeled data, allowing BERT to adapt to various NLP tasks with minimal task-specific data. Versatility. BERT has demonstrated its versatility across a wide range of NLP tasks, including text classification, named entity recognition, question answering, sentiment analysis, and more. Its ability to generate contextually rich representations make it suitable for diverse applications in both research and industry. Overall, Bert has established itself as a foundational model in the field of NLP, setting new standards for language understanding and driving advancements in various downstream applications. Its impact continues to be felt across academia and industry, inspiring further research and innovation in natural language processing. Understanding transformers. Transformer architecture. The transformer architecture introduced in the paper Attention is All You Need by Vaswani et al. In 2017 is a neural network architecture specifically designed for sequential data processing, such as natural language processing tasks. Unlike traditional recurrent neural networks (RNNs) or convolutional neural networks (CNNs), which rely on recurrence of convolution for sequence modeling, the transformer architecture relies solely on attention mechanisms. The key components of the transformer architecture include encoder. The encoder processes the input sequence and generates a sequence of hidden representations. Each input token is embedded into a high-dimensional vector space and passed through multiple layers of self-attention and feed-forward neural networks. The output of the encoder is a sequence of context-aware representations for each input token. Decoder. The decoder takes the output of the encoder and generates the output sequence. Similar to the encoder, the decoder consists of multiple layers of self-attention and feed-forward neural networks. However, in addition to self-attention, the decoder also incorporates cross-attention mechanisms to attend to the encoder's output. This allows the decoder to generate output tokens based on both the input sequence and previously generated tokens. Self-attention mechanism. The self-attention mechanism is a key component of the transformer architecture that enables the model to weigh the importance of different tokens in a sequence when generating representations. It allows each token to attend to all other tokens in the sequence, capturing long-range dependencies and contextual information effectively. The self-attention mechanism operates as follows: query, key, and value. For each input token, 3 vectors are computed: query, key, and value. These vectors are linear projections of the input token embeddings. Attention scores. The attention score between 2 tokens is computed by taking the dot product of the query vector of one token and the key vector of another token, followed by a softmax operation to obtain a probability distribution overall tokens in the sequence. Weighted sum. The value vectors of all tokens are weighted by their corresponding attention scores and summed together to produce the output representation for each token. Multi-head attention. To capture different types of information and improve model performance, self-attention is typically performed in parallel across multiple heads, each with its own set of query, key, and value projection. The output representations from different attention heads are concatenated and linearly transformed to produce the final output. Transformer encoder versus decoder. While both the transformer encoder and decoder share similar architectural components, they serve different purposes in the overall model. Encoder. The encoder processes the input sequence and generates a sequence of hidden representations. It consists of multiple layers of self-attention mechanisms and feed-forward neural networks. The output of the encoder is a sequence of context-aware representations for each input token. The encoder's role is to encode the input sequence into a fixed dimensional representation that captures its semantic and contextual information. Decoder. The decoder takes the output of the encoder and generates the output sequence. In addition to self-attention and feed-forward layers, the decoder also incorporates cross-attention mechanisms to attend to the encoder's output. This allows the decoder to generate output tokens based on both the input sequence and previously generated tokens. The decoder's role is to generate the output sequence token by token, conditioned on the input sequence and previously generated tokens. In summary, while the transformer encoder focuses on encoding input sequences into context-aware representations, the decoder focuses on generating output sequences based on the encoded input and previously generated tokens. Together, they form the core components of the transformer architecture for sequence-to-sequence tasks such as machine translation and text summarization. Pre-training and fine-tuning with BERT. Pre-training BERT. Pre-training BERT involves training the model on large corpora of text data using unsupervised learning objectives. The goal of pre-training is to enable BERT to learn general language representations by capturing linguistic patterns and relationships in the input text. Masked Language Model (MLM). In MLM, a certain percentage of the input tokens are randomly masked, replaced with a special mask token, and the model is trained to predict the original tokens based on the surrounding context. This encourages BERT to understand the bidirectional context of words and learn representations that capture semantic relationships. Next, sentence prediction (NSP). In NSP, BERT is trained to predict whether a pair of sentences appear consecutively in the original text or not. This task helps BERT learn to understand relationships between sentences and capture disclosure level information. During pre-training, BERT learns to efficiently encode text sequences into context-aware representations using multiple layers of self-attention and feed-forward neural networks. The pre-trained BERT model can then be fine-tuned on specific downstream tasks with labeled data. Fine-tuning BERT. Fine-tuning BERT involves taking the pre-trained BERT model and adapting it to perform a specific task with labeled data. This process allows BERT to leverage the knowledge learned during pre-training and specialize its representations for the task at hand. Task-specific data representation. Prepare the labeled data for the downstream tasks such as text classification, named entity recognition, or question answering. Convert the input data into the format expected by BERT. Tokenization. Fine-tuning architecture. Depending on the task, additional layers of modifications may be added on top of the pre-trained BERT model to tailor it to the specific task requirements. For example, for text classification tasks, a classification layer may be added on top of the BERT model to predict the class labels. Fine-tuning procedure. Train the modified BERT model on the task-specific data using supervised learning techniques. Adjust the parameters of the BERT model and the additional task-specific layers based on the training data to minimize the task-specific loss function. Evaluation. Evaluate the fine-tuned model on a separate validation or test set to assess its performance on the target task. Fine-tune the model further if necessary to improve performance. By fine-tuning BERT on specific tasks, it can achieve state-of-the-art performance across a wide range of NLP tasks, including text classification, named entity recognition, question answering, sentiment analysis, and more. Transfer learning with BERT. Transfer learning with BERT refers to the process of leveraging the pre-trained BERT model to improve performance on downstream tasks with limited labeled data. By pre-training BERT on large corpora of text data using unsupervised learning objectives. BERT learns general language representations that capture syntactic and semantic relationships in text. Transfer learning with BERT involves fine-tuning the pre-trained BERT model on task-specific data, allowing it to adapt its representations to the target tasks. This approach is particularly beneficial when labeled data for the target task is scarce or expensive to obtain, as it enables BERT to leverage the knowledge learned during pre-training to achieve better performance with less labeled data. Transfer learning with BERT has been widely adopted in both research and industry, enabling practitioners to build high-performance NLP models with minimal task-specific data and resources. It has democratized access to state-of-the-art NLP technology and accelerated progress in various NLP applications. BERT architecture, input representation. In BERT, input sequences are first tokenized into individual tokens and special tokens are added to mark the beginning, CLS, and separation, SEP, of sentences. These tokens, along with the original input tokens, are then converted into embeddings using an embedding layer. BERT uses word piece tokenization, which breaks words into subwords and allows the model to handle out of vocabulary words more effectively. The input embeddings are then augmented with positional encodings to provide information about the position of each token in the sequence. This allows BERT to capture the order of tokens, which is crucial for understanding the context of the input sequence. Transformer layers. BERT consists of multiple layers of transformer encoders stacked on top of each other. Each transformer encoder layer consists of two sublayers. Self-attention layer. This layer computes attention scores between all pairs of tokens in the input sequence, allowing each token to attend to every other token in the sequence. Self-attention helps BERT capture long-range dependencies and contextual information effectively. Feed-forward neural network. After self-attention, the output representations of each token pass through a feed-forward neural network with a GELU, Gaussian Error Linear Unit, activation function. This layer applies a non-linear transformation to the representations, allowing BERT to learn complex patterns in the data. The output of each transformer encoder layer is a sequence of context-aware representations for each token in the input sequence. These representations capture rich semantic and contextual information, allowing BERT to understand the meaning of the input text effectively. Output layer. The output layer of BERT varies depending on the specific task being performed. For tasks such as text classification or named entity recognition, a classification layer is added on top of the pre-trained BERT model. This classification layer typically consists of a simple feed-forward neural network followed by a softmax activation function, which produces probability distributions over the possible output labels. For tasks such as question answering or text generation, the output layer may involve additional processing steps such as span prediction or sequence generation to produce the final output. Overall, the BERT architecture combines self-attention mechanisms with feed-forward neural networks to encode input sequences into context-aware representations effectively. This architecture has proven to be highly effective across a wide range of natural language processing tasks, achieving state-of-the-art performance on various benchmarks and datasets. Word piece tokenization. Word piece tokenization is a subword tokenization technique used in BERT to handle out of vocabulary words and improve the model's converge of the vocabulary. unlike traditional tokenization methods that split text into words based on white space or punctuation. Word piece tokenization breaks words into smaller sum-word units called tokens. The word piece tokenizer maintains a fixed size vocabulary of sub-word units, each representing a common subsequence of characters in the input text. During tokenization, the tokenizer greedily matches the longest possible subword unit from the vocabulary for each word in the input text. If a word cannot be entirely represented by any subword unit in the vocabulary, it is further split into smaller subword units. This approach allows Bert to effectively handle rare or unseen words by decomposing them into smaller units that are more likely to appear in the vocabulary. It also enables the model to capture morphological and semantic similarities between words, leading to better generalization performance. Special tokens in Bert. In addition to the tokens representing words and subword units, Bert introduces several special tokens to facilitate various aspects of the model, architecture, and training process. These special tokens serve specific purpose and are added to the input. Sequences during tokenization. CLS token. The CLS classification token is inserted at the beginning of each input sequence. It is used to represent the entire sequence when performing tasks such as text classification or sentence level classification. The final hidden state corresponding to the CLS token is used as an aggregate representation of the input sequence for downstream tasks. Separate token. The SCP separator token is inserted between pairs of sentences in the input sequence, indicating the boundary between sentences. It is also used to mark the end of the input sequence. The separator token helps Bert distinguish between multiple segments of text, such as sentence pairs in tasks like question answering or natural language inference. Mask token. The mask token is used during pre-training for the masked language modeling (MLM) objective. During pre-training, a certain percentage of the input tokens are randomly replaced with the mask token, and the model is trained to predict the original tokens based on the surrounding context. The mask token allows Bert to learn bidirectional representations of the input text by considering both the left and right context. Pad token. The padding token is used to pad sequences to a fixed length during mini batch training. Since Bert processes input sequences in mini batches, sequences within a batch are padded to the length of the longest sequence in the batch to ensure consistent input dimensions. The pad token is typically added at the end of sequences to fill any empty positions. These special tokens play a crucial role in Bert's architecture and training process, enabling the model to perform various tasks and learn contextual representations effectively. They allow Bert to handle diverse types of input sequences and extract meaningful information from them for downstream tasks. Bert pre-training tasks. Masked language model (MLM). The masked language model (MLM) is one of the pre-training objectives used in Bert to train the model to understand and generate language representations. In the MLM task, a certain percentage of the input tokens are randomly masked, meaning they are replaced with a special mask token. The model is then trained to predict the original masked tokens based on the surrounding context. The MLM objective encourages Bert to learn bidirectional representations of the input text by considering both the left and right context of each token. By predicting masked tokens, Bert learns to fill in missing pieces of text and understand the relationships between words in sentence. This enables the model to capture semantic and syntactic information effectively and generate contextual rich representations of language. During pre-training, Bert is trained on large corpora of text data using the MLM objective. By learning to predict masked tokens, Bert learns to generate meaningful representations of text that capture the semantics and syntax of the input language. These pre-trained representations can then be fine-tuned on specific downstream tasks with labeled data to adapt Bert to various natural language processing tasks. Next sentence prediction, NSP. The next sentence prediction NSP task is another pre-training objective and in Bert to train the model to understand the relationships between sentences in a document. In the NSP task, Bert is presented with pairs of sentences and trained to predict whether the second sentence follows the first sentence in the original text or not. During pre-training, Bert is fed pairs of sentences along with a special CLS token at the beginning of the input sequence to represent the entire pair. The model is trained to predict a binary label indicating whether the second sentence is a consecutive continuation of the first sentence or not. The NSP task helps Bert learn to understand discourse level information and capture relationships between sentences in a document. By predicting whether sentences are consecutive or not, Bert learns to encode information about document structure and discourse coherence. This enables the model to generate contextually relevant representations of text that capture not only the meaning of individual sentences but also the relationships between them. Overall, the combination of the MLM and NSP pre-training tasks allows Bert to learn comprehensive representations of language that capture both word level and sentence level semantics. These pre-trained representations serve as a strong foundation for adapting Bert to various downstream natural language processing tasks with minimal task specific data. Applications of Bert. Text classification. Bert has been widely used for text classification tasks where the goal is to categorize text into predefined classes or categories. Whether it's classifying news articles, social media posts, or product reviews, Bert's contextual understanding of language allows it to capture nuanced features in the text, leading to improved classification performance. Named Entity Recognition (NER). Named Entity Recognition is the task of identifying and classifying named entities such as people, organizations, locations, dates, and more within text. Bert's ability to capture contextual information helps excel in NER tasks by understanding the context in which named entities appear, leading to more accurate recognition and classification of entities. Question answering. Bert has been successfully applied to question answering tasks where the goal is to generate accurate answers to questions based on a given context or passage. By fine-tuning Bert on question-answer datasets such as SQUAD, Stanford Question Answering Datasets, Bert can effectively understand the context of the question and generate precise answers, outperforming previous models on various question-answer benchmarks. Sentiment analysis. Sentiment analysis involves determining the sentiment or opinion expressed in a piece of text, such as positive, negative, or neutral. Bert's contextual understanding of language enables it to capture subtle nuances and contextual cues in the text, making it well suited for sentiment analysis tasks. By fine-tuning BERT on sentiment analysis datasets, it can accurately classify the sentiment of text with high accuracy. Semantic similarity. Semantic similarity tasks involve measuring the degree of similarity or relatedness between two pieces of text, whether it's determining the similarity between sentences, paragraphs, or documents. BERT's contextual embeddings enable it to capture semantic relationships between pieces of text effectively. By fine-tuning BERT on semantic similarity datasets, it can produce accurate similarity scores that reflect the semantic relatedness between text pairs. Overall, BERT's versatility and effectiveness across various natural language processing tasks have made it a go-to model for a wide range of applications, from text understanding and classification to information retrieval and conversational artificial intelligence. Its ability to capture contextual information and generate high-quality representations of language has led to significant improvements in performance across different domains and use cases. BERT variants and improvements. Distilled BERT. Distilled BERT is a distilled version of BERT developed by Hugging Face. It retains much of the architecture and functionality of BERT but is smaller and faster, making it more suitable for deployment in resource-constrained environments. Distilled BERT achieves this by using a smaller model size, fewer layers, and parameter sharing techniques during training, resulting in a significant education in memory footprint and inference time while maintaining comparable performance to BERT on various NLP tasks. Roberta, robustly optimized BERT approach. Roberta is an extension and improvement of the original BERT model developed by Facebook Artificial Intelligence. It incorporates several modifications and optimizations to the pre-training process, including larger training datasets, longer training sequences, dynamic masking patterns, and removing the next sentence prediction (NSP) task. These changes result in more robust and generalized language representations, leading to improved performance on a wide range of NLP tasks compared to BERT. Albert, a light BERT. Albert is a variant of BERT introduced by Google Research that focuses on reducing the model size and computational requirements while maintaining or improving performance. Albert achieves this by using parameter sharing techniques, factorized embedding parameterization, and cross-layer parameter sharing. The optimizations enable Albert to achieve better parameter efficiency and scale to larger model sizes without significantly increasing computational costs, making it more efficient for training and deployment in practical scenarios. Electra, efficiently learning and encoder that classifies token replacements accurately. Electra is a novel pre-training approach introduced by Google Research that replaces the MLM task used in BERT with a more efficient and effective task called replaced token detection (RTD). In the RTD task, a small percentage of input tokens are randomly replaced with incorrect tokens, and the model is trained to distinguish between the original and replaced tokens. This adversarial training approach allows Electra to learn more discriminative representations of text and achieve better performance compared to BERT with fewer pre-training steps and computational resources. XLNet. XLNet is a state-of-the-art language model introduced by Google Research that extends the transformer XL architecture with auto-regressive pre-training and permutation based language modeling objectives. Unlike BERT, which used a unidirectional or masked language modeling (MLM) objective, XLNet leverages permutations of the input sequence to capture bidirectional context during pre-training. This allows XLNet to model dependencies between all tokens in the input sequence and capture long-range dependencies more effectively, leading to improved performance and various NLP tasks compared to BERT and other models. These variants and improvements of the original BERT model demonstrate ongoing research efforts to enhance the efficiency, performance, and generalization capabilities of pre-trained language models for various natural language processing tasks. Each variant offers unique advantages and trade-offs, providing researchers and practitioners with a diverse set of tools for building high-performance NLP systems. Training BERT models. Training BERT models involves several key steps from data pre-processing to fine-tuning on specific tasks. Here is an overview of the training process. Data pre-processing. Prepare the training data for BERT by tokenizing the text into individual tokens using word-piece tokenization. Convert the tokens into input embeddings and add special tokens like CLS and SCP as necessary. Pad or truncate sequences to a fixed length to create uniform input sequences. Pre-training. Train the BERT model on a large corpus of text data using unsupervised pre-training objectives such as masked language modeling (MLM) and next sentence prediction (NSP). During pre-training, the model learns to generate contextually rich representations of words and sentences by capturing bidirectional context and semantic relationships in the text. Fine-tuning. Fine-tune the pre-trained BERT model on specific downstream tasks with labeled data. This involves adding task-specific layers on top of the pre-trained BERT model and training the entire model on task-specific data using supervised learning techniques. Adjust the parameters of the BERT model and the additional task-specific layers based on the training data to minimize the task-specific loss function. Hyperparameter tuning. Experiment with different hyperparameters such as learning rate, batch size, optimizer, and dropout rate to optimize the performance of the fine-tuned BERT model. Use techniques like grid search or random search to find the optimal hyperparameters for the target task and dataset. Regularization. Apply regularization techniques such as dropout or weight decay to prevent overfitting during training. Regularization helps improve the generalization performance of the model and reduces the risk of memorizing noise or outliers in the training data. Monitoring and logging. Monitor the training process using evaluation metrics and logging utilities to track the model's performance and detect potential issues such as overfitting or vanishing gradients. Visualize training curves and metrics over time to identify trends and make informed decisions about model training. Model checkpointing. Save checkpoints of the model's parameters periodically during training to allow for model recovery in case of unexpected failures or interruptions. Checkpointing ensures that valuable training progress is not lost and enables the model to resume training from the last saved state. Training infrastructure. Train BERT models on powerful hardware accelerators such as GPUs or TPUs to speed up training and reduce training time. Utilize distributed training frameworks and cloud computing platforms to scale training across multiple devices or machines for efficient use of resources. Overall, training BERT models requires careful attention to data pre-processing, model architecture, hyperparameter tuning, regularization, and training infrastructure to achieve optimal performance on specific NLP tasks. Evaluation matrix. Evaluation matrix are used to assess the performance of BERT models on various natural language processing tasks. The choice of evaluation matrix depends on the specific task and the desired performance characteristics. Here are some commonly used evaluation matrix for different NLP tasks. Accuracy. Accuracy is a simple and intuitive metric for classification tasks that measures the proportion of correctly classified instances out of the total number of instances in the dataset. It is calculated as the number of true positives and true negatives divided by the total number of instances. Mean absolute error, MAE. MAE is another metric for regression task that measures the average absolute difference between the predicted and actual values like MSE. Lower MAE values indicate better model performance. F1 score precision, recall for NER. For named entity recognition tasks, F1 score, precision, and recall are commonly used evaluation metrics. These metrics assess the model's ability to correctly identify named entities precision, capture all named entities recall, and provide a balanced measure of both F1 score. Blue score, BLEU, bilingual evaluation understudy, is a metric used to evaluate the quality of machine-generated translations in machine translation tasks. It compares the generated translation against one or more references translations and computes a score based on the n-gram overlap between them. Rogue score, rogue, recall-oriented understudy for gisting evaluation, is a metric used to evaluate the quality of text summarization by comparing the generated summary against one or more reference summaries. It computes scores based on the overlap of n-grams, word sequences, or word usage between the generated summary and reference summaries. Semantic similarity matrix. For tasks involving semantic similarity of relatedness, evaluation matrix such as Pearson correlation coefficient, Spearman's rank correlation coefficient, or consign similarity are commonly used to assess the similarity between model predictions and human judgments. Overall, the choice of evaluation matrix depends on the specific task, dataset, characteristics, and the desired performance criteria. It is essential to select appropriate evaluation matrix that align with the task objectives and provide meaningful insights into the model performance. Additionally, it is common to use multiple evaluation metrics to obtain a comprehensive understanding of the model's strengths and weaknesses. Deploying BERT models into production involves several considerations to ensure efficient, scalable, and reliable performance in real-world applications. Here are key aspects to consider. Deployment considerations. Infrastructure. Choose a deployment environment that provides sufficient computational resources to run BERT models efficiently. Cloud-based platforms like AWS, Google Cloud, or Azure offer scalable infrastructure options, including GPUs and TPUs, for deploying deep learning models like BERT. Model serving. Use a scalable and reliable model serving framework to deploy BERT models in production. Frameworks like TensorFlow Serving, TensorFlow Extended TFX, or TorchServe provide robust deployment solutions with support for model versioning, monitoring, and serving multiple models simultaneously. Concurrency. Consider the expected workload and concurrency requirements when deploying BERT models. Ensure that the deployment environment can handle concurrent requests efficiently to avoid performance bottlenecks and maintain low latency. API design. Design a well-designed API for interacting with BERT models in production. Use standard protocols like RESTful APIs or gRPC to expose model inference endpoints and define clear input and output formats for interacting with the model. Security. Implement security measures to protect the deployed BERT models from unauthorized access and potential attacks. Use authentication and authorization mechanisms to control access to the model endpoints and encrypt sensitive data transmitted between clients and the server. Scalability. Horizontal scaling. Deploy BERT models across multiple instances or servers to handle increasing workload demands. Use load balancers or distributed processing frameworks to distribute incoming requests evenly across the deployment environment and ensure scalability. Batch processing. Optimize BERT model inference by processing multiple requests simultaneously using batch processing techniques. Batch processing reduces the overhead of loading and running the model for each individual request, improving overall throughput and scalability. Asynchronous processing. Implement asynchronous processing to handle long-running or resource-intensive requests efficiently. Asynchronous processing allows the server to handle multiple requests concurrently without blocking the main execution thread, enabling better resource utilization and scalability. Caching. Use caching mechanisms to store and reuse frequently requested results from the BERT model. Caching reduces the computational overhead of processing redundant requests and improve response times, especially for repetitive or predictable query patterns. Performance optimization. Model quantization. Apply model quantization techniques to reduce the memory footprint and computational requirements of BERT models. Quantization techniques like weight quantization, activation quantization, or hybrid quantization can significantly improve inference speed and memory efficiency without sacrificing model accuracy. Model pruning. Prune redundant or low impact parameters from the BERT model to reduce its size and improve inference speed. Model pruning techniques identify and remove unnecessary connections or parameters from the model while preserving its performance, resulting in smaller and more efficient models. Hardware acceleration. Leverage hardware accelerators like GPUs or TPUs to accelerate BERT model inference and improve overall performance. GPU-based deployments offer significant speedups for deep learning workloads, while TPUs provide specialized hardware optimized for TensorFlow-based models like BERT. Model optimization libraries. Utilize model optimization libraries and tools like TensorFlow Model Optimization Toolkit or PyTorch JIT just-in-time compiler to optimize BERT models for deployment. These tools offer a wide range of optimization techniques, including quantization, pruning, and kernel fusion to improve inference speed and reduce memory usage. Profiling and tuning. Profile the BERT model's performance during deployment to identify bottlenecks and areas for optimization. Use profiling tools to analyze CPU, memory, and GPU utilization and fine-tune model hyperparameters or deployment configurations to maximize performance and efficiency. By addressing deployment considerations, ensuring scalability, and optimizing performance, BERT models can be effectively deployed into production environments, enabling real-world applications to benefit from the capabilities of state-of-the-art natural language processing models. Challenges and limitations. Training data size. Limited labeled data. One of the primary challenges in training BERT models is the availability of large-scale labeled data for pre-training and fine-tuning. While BERT can leverage unsupervised pre-training on large text corpora, fine-tuning on task-specific labeled data often requires substantial amounts of annotated examples, which may be costly or time-consuming to obtain. Data imbalance. Imbalanced datasets can pose challenges during fine-tuning, leading to biased model predictions and poor generalization performance. Addressing data imbalance through techniques like data augmentation, oversampling, or class weighting is crucial for improving model robustness and fairness. Computation resources. Computational complexity. BERT models are computationally intensive and require significant computational resources, memory, and training time, especially for large-scale models with millions of parameters. Training and deploying BERT models on hardware accelerators like GPUs or TPUs can mitigate computational challenges but may still require substantial infrastructure investments. Scalability. Scaling BERT models to handle large-scale datasets or high concurrency workloads can be challenging due to limitations in hardware resources, network bandwidth, and distributed computing frameworks. Optimizing model architectures, parallelizing computations, and implementing efficient data pipelines are essential for achieving scalable deployments. Domain adaptation. Domain-specific knowledge. BERT models trained on general text corpora may lack domain-specific knowledge or vocabulary required for specialized tasks or domains. Fine-tuning BERT on task-specific data can improve performance, but domain adaptation challenges may persist, particularly for niche domains with limited training data. Transferability. While transfer learning with BERT enables knowledge transfer from pre-trained representations to downstream tasks, the transferability of learned features may vary across domains and tasks. Fine-tuning strategies, data augmentation techniques, and domain adaptation methods are essential for maximizing transferability and adapting BERT models to diverse application domains. Addressing these challenges and limitations requires interdisciplinary efforts in machine learning, natural language processing, and domain-specific knowledge. Research advancements in data-efficient learning, model compression, transfer learning, and domain adaptation techniques are critical for overcoming these challenges and unlocking the full potential of BERT and similar deep learning models in real-world applications. Resources and tools. BERT GitHub repository. Link: BERT GitHub repository. Description: the official GitHub repository for BERT, maintained by Google Research. It contains the source code, pre-trained models, and script for pre-training and fine-tuning BERT models. The repository also includes documentation examples and tutorials for using BERT in various natural language processing tasks. Hugging Face Transformers Library. Link: Hugging Face Transformers. Description: the Transformers library by Hugging Face provides a higher-level interface and pre-trained models for working with state-of-the-art natural language processing models, including BERT, GPT, Roberta, and more. It offers easy-to-use APIs for loading pre-trained models, fine-tuning on custom datasets, and performing inference on a wide range of NLP tasks. Bert research papers. Bert, pre-trained of deep bidirectional transformers for language understanding. This seminal paper by Jacob Devlin, ETAL, published in 2018, introduced the Bert model and its pre-trained objectives, including masked language modeling and next sentence prediction. It provides detailed insights into the architecture, training process, and evaluation results of Bert on various natural language understanding tasks. Roberta, a robustly optimized Bert approach. The Roberta paper by Yinhan Liu et al., published in 2019, presents improvements and optimizations to the original Bert model, leading to better performance and robustness across a wide range of NLP tasks. It introduces modifications to the pre-training objectives, training data, and hyperparameters, resulting in state-of-the-art performance on benchmarks like GLUE and SQuAD. Albert, a light Bert for self-supervised learning of language representations. The Albert paper by Zhenzong Lan et al., published in 2019, introduces Albert, a variant of Bert designed to reduce model size and computational requirements while maintaining or improving performance. It presents techniques such as parameter sharing, factorized embedding parameterization, and cross-layer parameter sharing to optimize the Bert architecture for efficiency and scalability. Electra, pre-training text encoders as discriminator rather than generators. The Electra paper by Kevin Clark et al., published in 2020, introduces the Electra model, which replaces the masked language modeling objective used in Bert with a more efficient and effective task called replaced token detection (RTD). It presents adversarial training techniques for training Electra, resulting in better model efficiency and performance compared to Bert. XLNet, generalized autoregressive pre-training for language understanding. The XLNet paper by Zuiling Yang et al., published in 2019, introduces XLNet, a state-of-the-art language model that extends the transformer XL architecture with autoregressive pre-training and pre-mutation-based language modeling objectives. It demonstrates improved performance on various NLP tasks compared to Bert and other models by capturing bidirectional context and long-range dependencies more effectively. These resources and tools provide valuable insights, implementations, and pre-trained models for working with Bert and advancing research and applications in natural language processing. Text classification, sentiment analysis in movie reviews. You can use Bert to analyze sentiment in movie reviews by fine-tuning a pre-trained Bert model on a dataset of labeled movie reviews. Given a movie review as input, the Bert model can classify the sentiment of the review as positive, negative, or neutral based on the contextual information captured in the text. Spam detection in emails. Bert can also be used for spam detection in emails by training a binary classifier to distinguish between spam and non-spam emails. By fine-tuning a pre-trained Bert model on a dataset of labeled emails, the model can learn to identify patterns and linguistics cues indicative of spam content, enabling accurate detection of spam emails. Named Entity Recognition (NER) recognition entities in text. Bert can be employed for named entity recognition (NER) tasks to identify and classify entities such as names, dates, locations, organizations, and more in text. By fine-tuning a pre-trained BERT model on a labeled dataset of named entities, the model can learn to recognize and classify different types of entities with high accuracy. Question answering. Answering question from text passages. BERT can be implemented for question answering tasks by fine-tuning a pre-trained BERT model on a dataset like SQUAD, Stanford Question Answering Dataset. Given a question and a passage of text containing the answer, the BERT model can generate accurate answers to the questions based on the contextual understanding of the text. Sentiment analysis. Analyzing social media posts. BERT can be applied to sentiment analysis tasks on social media posts to gauge public opinion or sentiment towards specific topics, products, or events. By fine-tuning a pre-trained BERT model on labeled social media data, the model can classify the sentiment of posts as positive, negative, or neutral, providing valuable insights for sentiment analysis and opinion mining. Semantic similarity. Calculating similarity between sentences, BERT embeddings can be used to calculate the semantic similarity between two sentences by measuring the cosine similarity of Euclidean distance between their BERT embeddings. By encoding the sentences into dense vector representations using a pre-trained BERT model, you can compare the similarity of sentences based on their semantic meaning, enabling applications like duplicate detection, paraphrase identification, and information retrieval.